Welcome to the video of area by double integral. So upon completion of this video, viewers should be able to use double integral to calculate the area of a bounded region as well as to find the average value of a function with two variables. Before we proceed with the area of a bounded region, let's take a look at the Riemann sums for volume. So this is the formula for the Riemann sums for volume. Div fxy is the height of the rectangular cuboid, and this delta A is the area of base of the rectangular cuboid. So if we take a look at only this singular rectangular cuboid, this will be the fxy, and the area of base of this rectangular cuboid will be the delta A. Delta A is the product of delta y and delta x. So if we increases the number of rectangular cuboids over here, just like this, we sum the volume of these rectangular cuboids up, we will get a volume closer and closer to the exact volume under this hemisphere. So as the number of these rectangular cuboids goes to infinity, we will get the exact volume of the region formed by this hemisphere. For the Riemann sum for area, instead of summing up all the rectangular cuboids, we are summing up all the rectangles formed under the graph this time. So as the number of these rectangulars goes to infinity, we can write this whole summation into this form: a double integral with respect to dA over the region R. Let's look at an example. In this example, we are asked to find the area of the region R enclosed by two graphs which are y equal to x squared and y equal to x plus 2. To get a clearer picture of the region, we can first sketch a graph, and if you look something like this. So the region we are asked to find is the region over here. We have seen that the formula to find the area is equal to double integral with respect to dA over the region R. And from Fubini's theorem, we can write in this form or this. In this form, we do the integration with respect to dx first and then to dy, while in this form we do the integration with respect to dy first and then to dx. So these are the limits for dx and these are the limits for dy. Note that when we switch the order of integration, we have to switch these limits as well. Sometimes the order of integration does matter. So if we want to find the area using this formula, our limit for x will be in unknowns and our limit for y will be in numbers, so that at the end of the integration we will get a number. So for this, our limits for y will be in unknowns form and our limit for x will be in numerical values. Let's do the integration with respect to dx first and then to dy. So as I have said earlier, our y limits will be in numerical form, and in this case it might be 0 for the lower limit and 4 for the upper limit. So our x, the limits for our x will be in terms of y. So if we change this equation in terms of y, we will get x equal to plus minus square root y, and this we will get x equal to y minus 2. So if we take positive square root y as the upper limit for x and y minus 2 as the lower limit for x, we will be fine, but only until y is equal to 1, because beyond this point we will include the area over here, which is not what we want because we just want to evaluate the area over here. So what we can do now is we break the whole region into these two parts. So we have to redefine our limits for y as well as x. This time our limit for y will be 1 for the lower limit and 4 for the upper limit, and our limit for x will be positive square root y for the upper limit and y minus 2 as the lower limit. Then after doing integration, we will get the area of this region. So for the lower part of this region, we have our limits for y 0 and 1, while the limits for our x will be positive square root y and lower limit will be negative square root y. Then we add the area of these two regions together and we will have the whole region. So our integration will look something like this. This will be the upper region and this will be the lower region. Next, let's take a look when we change the order of integration, which in this case we do the integration with respect to dy first and only then with respect to dx. So this time our limits for dx will be in numerical form and dy will be in terms of x. So we will have our integration like this. Obviously this is much more easier than this, and eventually if you do both integration we will arrive to the same answer. So let's just do this. After integrating with respect to dy and substituting the limits, we will get something like this, and we just do the integration with respect to dx, we will arrive to something like this, and we substitute the limits, we will get 2 square over 2 plus 2 times 2 minus 2 cube over 3 minus 1 square over 2 plus 2 times minus 1 minus 1 cube over 3. And if we evaluate everything, we will get the area equal to 9 over 2.
Alright, so now let's move on to the idea of average value. Before that, I want to apologize because I recently got a bit of a cold, so my voice might sound a bit nasal. I apologize for that. So to find the average value, you just have to find this double integral and divide it by the area of the base. So what does this formula all mean? Well, recall that the double integral gives you the total of all the rectangular cuboids in the graph, or more precisely, the total or the sum of all the rectangular cuboids as the number of the rectangular cuboids goes to infinity, which means that the base is infinitesimally small, if you could imagine. So you could imagine that this double integral gives you a sort of a 3D picture of hills and valleys, because for each fxy it could be different for each value of x and y, right? So that would give you sort of the picture of hills and valleys. So if you could think of that picture, right, then the idea of the average value comes easily, because you could sort of imagine it. Well, let's suppose that this fxy is defined under this the limits of, say, okay, let's say that this is a 3D picture of hills and valleys, and that this picture is bounded within 2 kilometers square, right? So in this 2 kilometers square, each of these hills and valleys have different heights, right? Some could be positive and some could be negative. So let's say you want to find the average value for each mountain. You want to know what's the mean of all of these hills and valleys, the height of each hills and valleys, with respect to, say, a meter square. So what you do is you find the double integral, which gives you this 3D picture of the hills and valleys, and then you divide it by the base. Well, the base is 2 kilometers square, but because you want to talk about it in terms of meters square, you divide it by 2 million meters square, because 2 million square is equal to 2 kilometers square, right? So we divide by it, and we'll get the average height of each of the picture. So we don't have to think of it as heights. We could extend it to temperature. So let's say in this example that fxy represents the temperature, and the variables are x and y. So the temperature of this thing is like this temperature is the temperature of the plate, which is this area R, right? So how do we find the average temperature? So, well, you could imagine it as a plate here, right? So this is a plate, and so let's say that this plate is made of different materials. So and this is like you put it in the oven, you take it out, right? And each part of it has different temperature. So let's say this region here is hotter, and this region here is hotter, and this region here is hotter. So you could think of it like this. And for each region that's hotter, right, you can imagine it sort of having higher temperature and higher value. So if you could graph it for the xy, you can imagine that this fxy is the height in the graph. So this temperature, for each increasing temperature, the height increases. So it sort of gives you this idea of hills and valleys, right? Then you just have to divide the area of base, and you can find the average value of this plate. Remember, this plate has varying temperature. We just find the average value of it. Right, so now let's move on to an example. So we're given the task to find the average value given this function e to the power of x plus y over the region of 0 to 2 and 0 to 2. So to find the average value, recall that the formula is find the double integral and divide it by the area of the base. So let's just do that. So to find the double integral, what we have to do is simple here. We will insert the fxy into this formula, so it's e to the power of x plus y, and the limit in terms of dx and dy. Remember Fubini's theorem, dx and dy doesn't matter here, and it's even more de-emphasized here because both of the limits are the same. So we find that the double integral is this, given by this formula here. So now let's find the area of the base. Well, the area of the base is just this, right? It's represented in this graph. So 2 times 2 is equal to 4. So we have found the area of the base. So putting it all together, we get this. Alright, so let's evaluate the average value here. So to solve this, right, we have to first do this partial integration, right? So what's the partial integration of this function here? Well, we have to find out the antiderivative of e to the power of x plus y, right? So we could use substitution here. So let u equal to x plus y. And you'll find out that this antiderivative of this function here is itself e to the power of x plus y. This is because we can treat the other variable, which is y here, as a constant. So what we'll get is this formula here. So next we just have to plug in this value here, this function with this value, and minus this function with this value. So we'll get this formula here. So the next step is to find out this partial integration over here. So what we have to do is we have to find this antiderivative of this function here. So what's the antiderivative of this? Well, we could separate this two into two parts, right? So what's the antiderivative of e to the power of 2 plus y? Well, similar to the previous case, it's itself e to the power 2 plus y, which is also the same case goes to e to the power of y. So what we'll get is this formula here, and this is basically done, right? We'll just have to evaluate it, plug in the 2 into y, and minus this function with y equals to 0. So we'll get this function here, e to the power of 4 minus 2 times the e to the power of 2 plus 1, and the whole thing divided by 4, and which is approximately equal to 10.2. So that's how you find the average value of a double integral.